a black hole that shouldn't exist, and it's right next door. They have discovered the second closest black hole to Earth, Gaia BH3. But this black hole is nearly 3.5 times more massive than the closest black hole discovered so far. And this size places it into a class of black holes that, according to what we previously knew, should not exist, at least within the framework of our current understanding of these particular black holes. This naturally raises a question in my mind. If such a massive black hole is practically right under our noses and we managed to overlook it for so long, what other black holes might be out there right now whose existence we are completely unaware of? Let's find out. First of all, this spectacular discovery was not made by NASA, but by the European Space Agency, ESA, and its Gaia Space Observatory, which was launched in 2013. Like the famous James Webb Space Telescope, Gaia orbits around a special gravitational region known as the L2 Lagrange point. This is one of 5 special gravitational equilibrium points formed by the interaction of the Sun's and Earth's gravitational fields. The L2 point around which Gaia orbits lies on the imaginary line connecting the Sun and Earth, on the side of Earth opposite the Sun, about 1.5 million kilometers away. Since the beginning of its mission, Gaia has achieved remarkable successes. For example, out of the roughly 400 billion stars in the Milky Way galaxy, Gaia has so far cataloged 1.7 billion of them with extremely high precision. And every year, we continue to discover numerous new exoplanets, galaxies, and stars. Astronomers usually prefer not to publish such vast amounts of data piece by piece. Instead, they compile all new findings into a catalog and release it every few years. For instance, Gaia's latest data release was published in 2022, and the next one is planned for 2025. However, the discovery of Gaia BH3 is so significant that astronomers chose to publish a dedicated paper immediately without waiting for the next catalog release. This is because research on this black hole needs to begin right away. Although Gaia BH3 is extraordinarily massive, it is actually among the smallest black holes ever discovered because it is not a supermassive black hole, but a stellar mass black hole. Yet within this category, it possesses an unprecedented mass, which makes it exceptionally special. As I've explained before, stars with masses 8 times that of the Sun or greater end their lives by exploding in a tremendous supernova once they exhaust their fuel. During this explosion, most of their matter and energy are ejected into space. The remaining material is compressed with such immense force that an enormous amount of matter is squeezed into a tiny volume. If the remaining mass exceeds the Tolman-Oppenheimer-Volkoff limit, which is about 2 to 3 solar masses, the stellar core continues collapsing and turns into one of the most mysterious objects in the universe, a black hole. If it is below this limit, a neutron star forms. However, there is something fewer people know. Just as there is a minimum mass required for a star to become a black hole, there is also a maximum mass. If a star is abnormally large, certain processes that occur weakly in smaller stars become far more violent, preventing the star from forming a black hole at all. For example, if a star is extremely large and also has high metallicity, meaning it contains a large proportion of heavier elements than hydrogen and helium, it develops very strong stellar winds. These winds cause gases in the star's upper atmosphere to be blown into space at high speeds. Yes, stars have atmospheres too, just like planets, and activity in these layers can determine a star's fate, much like Earth's atmosphere shapes Earth's destiny. In addition, other factors come into play. Extremely massive stars emit extraordinarily energetic radiation. Their corona can reach temperatures of millions of degrees, and plasma flows, driven by magnetic fields, similar to the coronal mass ejections we observe on the Sun, can occur. These winds can reach speeds of hundreds or even thousands of kilometers per second, allowing atoms in the stellar atmosphere to escape the star's gravitational pull and be flung into space. As a result, very massive stars, especially near the end of their lives, lose so much mass through these processes that they cannot produce the kind of supernovae required to leave behind very large black holes. Moreover, stars with masses between roughly 130 and 250 times that of the Sun can experience a special phenomenon known as a pair instability supernova. In such stars, the core becomes so hot and dense that high-energy thermal photons spontaneously create electron-positron pairs. These pairs steal energy from the photons that normally support the core against collapse, weakening that support and making the core increasingly unstable. In massive stars with weakened cores, the resulting supernovae are so destructive that nothing remains to form a black hole. All material is completely dispersed into space. For all these reasons, for a long time we believed that stellar mass black holes formed from dying stars could reach at most around 20 solar masses. Anything larger than this was thought to be impossible. Yet Gaia BH3, with a mass of 32.7 times that of the Sun, far exceeds this limit, hence why it was initially described as a black hole that should not exist. However, this is not the first anomalously massive stellar mass black hole we have encountered. You may recall that the biggest science news of 2015 when the LIGO interferometer detected gravitational waves produced by the merger of two black holes, an extraordinary confirmation of another key prediction of Einstein's general theory of relativity. A crucial detail that wasn't emphasized enough at the time is that one of those black holes had a mass of 29 solar masses, and the other 36 solar masses. As you can see, both exceed the previously assumed 20 solar mass upper limit for stellar black holes. Earlier, Cygnus X1 with about 21 solar masses had already hinted that such objects might exist, but it did not challenge the theoretical limit strongly enough to cause serious concern. LIGO's 2015 findings, however, made it clear that something else is going on. Understanding how stellar mass black holes form is critically important because we know very little about how supermassive black holes, like Gargantua in Interstellar or Sagittarius A1 at the center of our own Milky Way, came into existence. These are not merely 20 or 30 times the mass of the Sun. Sagittarius A1 alone is about 4 million solar masses, and others can be billions of times more massive. Most likely, these giants began their lives already massive, forming from extremely large metal-poor stars that were not strongly affected by stellar winds and collapsed directly into black holes, without even going through supernovae. Over billions of years, they grew even larger by merging with other black holes and accreting surrounding material. Research on this topic is still ongoing. Returning to today's focus, Gaia BH3 may not be a supermassive black hole, but it is just as fascinating and surprising. This stellar mass black hole, nearly 33 times the mass of the Sun, is located only 1,930 light-years away, and yet we are only discovering it now. To be clear, 1,930 light-years is still an enormous distance, about 2% of the Milky Way's diameter, so the chance of waking up one morning face-to-face with this black hole is practically zero. Even if we were traveling toward each other at the speed of light, which we are not, it would still take nearly 2,000 years to meet. Astronomical risks are never about events happening in 35 days or even a few kilometers away. Compared to everyday risks, Gaia BH3 poses no danger at all. In fact, Gaia has also discovered Gaia BH1, a black hole about 9.5 solar masses, only 1,560 light-years away. Still, these distances should not be underestimated. Even so, Gaia BH3 is the second closest known black hole to Earth, and in this region of the galaxy, what we might call our cosmic backyard, who knows how many other black holes have escaped our notice. More importantly, discoveries like Gaia BH3 help us better understand the conditions under which stars exceeding 20 solar masses can still form stellar mass black holes. One key factor is stellar metallicity. The fewer heavier elements a star contains, the less it is affected by stellar winds. Interactions with other stars before death also play a role. In binary systems, one star can strip away the outer layers of its companion, allowing stars that would normally not form black holes to collapse into one. Indeed, Gaia BH3 is part of a binary system. One object is the black hole itself, and the other is a red giant, a very large, very bright, and coincidentally, metal-poor star. This companion is precisely what allowed us to detect the black hole. Black holes emit virtually no light, aside from a hypothetical trace of Hawking radiation, making them nearly invisible against the dark background of space. Therefore, we detect them by observing anomalies in the orbits of nearby luminous stars. If a star is orbiting something we cannot see, that something might be a black hole. By analyzing deviations in the star's motion, we can calculate the mass of the unseen object, then focus our instruments on that region to confirm the black hole through gravitational lensing effects. Gaia BH3 shows no surrounding accretion disk, meaning it is not actively feeding. This is why it remained hidden for so long. All evidence suggests that the black hole formed long before it captured its companion.